Hello, everyone, and welcome to the experimental design lecture. Today is Monday, the 18th of May, 2026, and we are going to discuss the following subjects today. We are going to look at the software for design of experiments, and we are going to carry out some examples and some exercises in order for you to better understand how this works. So first of all, let me share my screen with you. Okay, okay, okay. So I am going to share my screen. Perfect. So this is the a Word document, a new Word document. So I am going to save it as, let us put here. It is going to be the experimental design lecture and today's date, which is 18th May 2026. Save. Perfect. Okay. Well, so let us start. So we are in the experimental design. The lecture. Okay. My name is David Joaquin Delgado Hernandez, as the British say, Hernandez. The program is the Bachelor in Science, in Artificial Intelligence at the Autonomous University of the State of Mexico. Okay. Then the duration is 180 minutes. Language, it is in English. And the date, today's date, it's again the 18th of May, the 2026. Perfect. Okay. What are the subjects and the objectives for today's lecture? So the subject, 3.5, which is the statistical software. Here the objective is to select, utilize, and compare professional statistical software tools, for instance, such as, well, you can use many of them. I am going to put here some examples, such as Python, libraries, Matlab. It is the one that we are going to use, R, You can use Minitab. You can use expert design. You can use SPSS, which is statistical program for the social sciences. And you can even use Excel. Excel. In fact, we already have used Excel in some previous classes, right? These packages, okay, okay. This is for the automated generation and analysis of experimental design. That is the first subject for today. So I am going to put this in bold. Okay. Then the following subject, it is 4.1, which is the introduction to case studies. And here the objective is to analyze the, well, in this case, it is the physical and electronic characteristic. This is based on the Dr. Sala's book, Characteristics of the Three Experimental Systems. Experimental systems. You said in the book. I am going to change this for use it in the lecture. We are going to analyze the three cases, which is the paper airplane. The second is the mouse trap car. And the third is related to the concrete beam, the one of the first partial exam, okay? Okay. To establish the technical baseline for advanced experimental design application. Here we are. Perfect. So let me put this in bold again. Okay. Here. So I am going to put here in bold. And the third subject for today's class, it is 4.2. It is the identification. People, I have to tell you that the following Monday, the 25th of May, we are not going to have class because the university has decided that that is going to be a bank holiday. That means that we are not working. We are not having lectures on that day. You are not going to have any lecture. And I have already sent to you the document where this is specified. So please look at your WhatsApp in order to check. The idea is that we are going to celebrate Father's Day. Do you know the Mother's Day is the 10th of May, and now we are going to celebrate the Father's Day on Monday, the 25th of May. So this is a decision of the university. So we are having today this class, and the next one will be in 2 weeks' time. Okay, our next lecture will be on Monday. Let me check. I think that it will be already June, the 1st of June. That will be our next lecture and the last one of this term, right? 2026 8. That will be the last one. What I would like to ask you is for you to upload your concept map as usual in the Teams platform, and I am going to evaluate that. But we are going to have the last two lectures together the following Monday, June the 1st. Okay. Okay. So identification of variables and case studies. Okay. What is the objective here? It is to integrate all the experimental design concepts learned so far to identify, classify, and prioritize the variables of a system, establishing a robust experimental framework for artificial intelligence model characterization. Okay, so this is the third subject for today's lecture. Okay. Okay, so let us now start with the following table. Okay, so I am going to insert a table. So we are going to analyze our three case studies. So it's case study. The first one is going to be the paper airplane. Or folder. Okay. The second one has to do with the mouse trap car. And the last one is related to the concrete beam. Perfect. Let me put this like this. Okay, perfect. Okay. So here we are going to put different type of experiments in order for you to have a complete view of the kind of experiments that you can use in the professional practice experiment, the type of experiment and the objective. Okay. So the type of experiment here, we are going to carry out a full factorial 2 to the power k. So let's put here this as a power. This is a power. And here the objective is to look at the main effects and interactions of the variables. In the second case study, we are going to use a fractional factorial design and we are going to use the regression technique. And here the objective is to optimize is the optimization with multiple variables. And finally, we are going to use the response surface method which is acronym is RSM. And here the idea is to analyze the curvature and optimization and prediction. Very good. So let me save this. Okay. Well, so in the introduction, we can say that the artificial intelligence models are actually experiments. Okay. So every time that we change parameters, architectures, data sets, or sensors, we are designing an experiment. Experiments. Okay, so every time that we carry out some modification, what we are actually doing is that we are carrying out a new experiment. So design of experiments helps us discover which variables truly matter, what are the important variables, and how they interact, and how to optimize systems with fewer tests. Okay. So, well, these kind of experiments are very helpful for, this is useful, for instance, with a neural network tuning, sensor calibration, many things, right? Robotics, smart manufacturing. So there are so many different applications, autonomous systems, and so on. Okay. So the idea here then is to recognize that in artificial intelligence, every time that we carry out an experiment, we modify something and we have a new result. That is very important information in order to improve our models. Okay, well, okay. So let us put here something about the MATLAB. There is some particular libraries that are useful for carrying out this design of experiments. So I am going to put here some of them. Let me put a table. This table, it is let's use 2 columns and let's use 8 rows. So let me put 8 and that's it. Okay, so here's the concept and here's the function, the MATLAB function. Okay, so mm, mm, mm. Let me put this beautiful. Okay, perfect. Okay, so we can have a full factorial design. And the command that we are going to use is full fact, open and close parentheses. The second has to do with a fractional factorial design. And the command for MATLAB is fact. Okay. Then the regression command is a fit linear model LM, and you open and close parentheses. The ANOVA, which is the analysis of variance, is just like that, ANOVA, and you open and close the parentheses. Okay, this is with MATLAB case. Okay. Uh, surface fitting. You can use fit. There are some others like contour plots. And the command is precisely contour. And you use F at the end, open and close parentheses. And one other which is very useful is related to the surface plots. Okay, surf, open and close. Okay. So let us try the case number 1, which is the paper airplane or folder, right? Folder. Okay. So let me put this in bold. Okay. Well, what is the objective here? Okay. The objective in this experiment is to determine which variables maximize flying distance or flight distance. Flight distance. Okay? Okay. Before we continue, I am going to put here let us put here 7 steps to carry out design of experiments. Okay, these are very important, and we are going to use these 7 steps 3 times because we are going to use them in the 3 case studies that we have at hand. Okay. So the first step is related to determining experimental objectives. Objectives. Okay. So basically, it is the problem statement. The problem statement. Okay. The second step is identifying the responses, which are the outputs, and the measurement system. How are we going to measure that? Perfect. The next step is again identifying the input factors to study along with their levels, okay? The levels of these factors. Okay. Number 4 is choosing the right design. Here we have to look at some things such as replication. We have to look at sample size. Another thing is randomization. Full factorial or fractional factorial design. Okay, perfect. Number 5 is running the experiment. Oh, sorry. Here, number 5 is running the experiments. Experiment number 6 is analyzing the results. Results. Here we can have something like ANOVA, the main effects, the interaction effects. And so on. And finally, the 7th point is the conclusions. Okay, the conclusions and interactions. Here we can we can repeat the process. If we don't get the results that we were looking for, we can repeat the process in order to start once and again, okay? Once more, until we get the expected results, okay? So let us apply this to our three cases. So let me put this here. So I am going to divide my Word document. So let me see here, divide. Mm, 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 mm. Mm. So divide. Mm, mm, mm. First, I'm going to save this. And here, let me see. Here, divide. Okay, I am going to put this line here. So I can see this all the time. Okay, so let us put this down there and this up here. Perfect. Okay, so here. So I am going to use these 7 steps systematically in order for you to see how in real life you should carry out an experiment, a design of an experiment. Okay. So let us put this in this way. So I am going to copy this, copy. So in the first case, step 1, step 1. So I am going to paste. So the first step is determining experimental objectives. What is the problem statement? Okay, so the objective here in the case 1, which is paper, airplane, or folder, the objective is to determine which variable maximizes flight distance. Okay, so let us now move on to the second step. The second step, I am going to copy and I am going to put step 2. This is step 2. And I am going to paste the step 2. Okay. Step number 2 here is to identify the response outputs and the measurement systems. So the response is the flight distance, and I am going to measure in meters. Okay, that is going to be my measure for response flight distance. Okay, step number 3. Step number 3 is related to, here I'm going to copy, and I am going to paste here, paste. Identify input factors to study along with levels. Okay, so let me include here a table with the factors. Okay, so I am going to introduce here a table. So let us put insert table. Table, which is here. Okay, so here are the factors. And here are the low level, which is represented by -1. We already saw this last lecture, and the high value, which is +1. So let's put +1. Okay. Okay, so wing length will be my first factor, and the low level will be 8 centimeters, and the high level will be 12. Perfect. Now the nose weight first it will be 0 grams and then 3 grams. This is the second factor. And finally, the third factor is related to the launch angle. Okay, so let us use 15 degrees. And the height will be 45 degrees. Okay, perfect. So let me put this in a beautiful way. This kind of table, I like it. Okay, so that is step number 3, identifying factors to study along with levels, 2 levels, low and high. Okay, step number 4. Step number 4 is choosing the right design. I am going just to put this here. So paste. Choosing the right design. Perfect. So I am going to use full factorial design with 2 replications. So this is 2 to the power 3, which is 8. Let me put it like this. This is power. So 2 refers to the low and high, and the 3 refers to the number of factors: wing length, nose weight, and launch angle. Okay, so 2 to the 3 means 8 different combinations, right? It is -1, -1, -1, the first one, then -1, -1, +1, that is the second, and so on. Okay, but since we have two replications, we are going to have 16 experiments in total. That is the right design. Okay, I am going to repeat 2 times the same measurement in order for me to have more data, more information. Okay, the following step number 5, which is up here, running the experiment. Step number 5. Okay. Okay, so let me put this here, save. So I am going to insert a table. Insert table. It is going to have columns. It will be 1, 2, 3, 4, 5 columns, and it will be 17 here. Okay. Okay. So this is the run. We are going to have 16, as I said, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Perfect. So here we are going to have the first factor, which is the wing length. Let's call A, which is the wing length. Factor B, which is the nose weight. And factor C, which is the launch angle. Okay, and here is the response Y, which is the flight distance. Flight distance. Okay, well. Okay, so let me put this in a beautiful way. Here we are. So again, remember, we have to put here -1. Let me put here -1, -1, -1. Okay. So in order to do it systematically, we are going to have -1, -1, -1, and here it will be 1, 1, 1, and 1. Okay, so here we are going to have -1, -1, 1, 1, -1, -1, 1, 1. Okay, and here we are going to have -1, 1, -1, 1, -1, 1, -1, 1. Okay, so I am going to repeat this because the first 8 experiments are for the first replication, and the from experiment 9 until experiment 16 are the second replication. So let us copy this and paste it here. It's exactly the same, okay? And we are going to have 2 replications. Okay. Perfect. So let me, I am going to put the the values of the distances. Okay, so let's imagine that I carry out the experiment and so on, and the first value is 2.1 meters. The second is 2.3, then 3.0, 3.2, then 2.4. Again, this information comes from the actual experiments, right? It is when I designed the airplanes and I launch the airplanes, I am starting recording these values. Okay, so the following 4.5, then 4.7, 3.1. So let me sorry, let me put this well, let me put this. This is 2.1 and 9 is 2.3. Sorry, 2.3. Let me put it again. Let me put it again. So I am going to put 1 and 1, 1 and 1. So 2.1, 2.3. Okay. The second experiment, it will be 3.0 here. I am going to erase this in order not to get confused. So erase. Okay. The second experiment. So first I record 3.0, and in the second replication, I record 3.2. That is the correct order, okay? Then the third experiment, 2.4, and here, down here, 2.5. Okay, the next one, 4.5, and then 4.7. Perfect. Well, the next one, 3.1 and 3.3. Then 5.0 and 5.1. Then 3.6, and then 3.7, and finally 6.2 and 6.4. Okay, perfect. Okay, this is my table of the experiments that I have designed and I have carried out. Okay, this is step number 5. So step number 6 is analyzing the results. So let me paste it. So I am going to leave this in blank because I have to carry out the experiment and the calculations. Finally, step number 7 is related to conclusions. Let me put conclusions, okay? Again, I am going to leave this in blank because we are going to carry out the exercise. Okay, so what I would like you to do now is for you to open your Matlab. All of you have a free account in the University of Matlab. Let me show you how to open it. So please follow me because we are going to carry out the experiment using a Matlab script, okay? So I am going to share. Okay. So open Google Chrome and go to Google. So this is going to be recorded, but try to follow the steps. So here in the Google, you are going to look for Matlab online Autonomous University of the State of Mexico. So you write these 3 words, Matlab online UAMX, and you put enter. And the first link, it says access to Matlab and Simulink for the Autonomous University of the State of Mexico. So you click here. And you are going to see that Matlab, because we have both the license, the university has paid for the license of Matlab, okay? So we all have the right to use this software because it has the license for the students and lecturers. So you can click here where it says, let's start session. You put here, and you are going to write your institutional email address. Okay. For instance, in my case, it is david.delgado@omx.mx. I am going to put here my institutional email address. If you put Gmail, Hotmail, Yahoo, or any other mail, this is not going to work. You have to use mandatory this OMX email address. Okay, so you have to put next. You have to introduce your password, and you put start session. Uh, Let me see if I changed my wait me wait a minute. Let me check what is my password for this platform. Anyone have already got into the Matlab, so he or she can share his or her screen.
Teacher, I have the same problem as you.
The same problem, right? The password is not working.
Yes.
Okay, so make sure that you use the correct password because you only have 3 trials. Okay, you only have 3 different opportunities to get into the sorry, because I have a different password. So let me put, I hope that this is the correct password. Oh. Somebody has passed this step. Make sure again to use the correct password. Okay, let me see. Oh, no, I have forgotten my password. Uh, uh, uh. Let me see. Uh, Let me see in my other computer. Wait a second. Because again, if I try this so many times, the problem is that this is going to block my account. So let me stop sharing this computer. I am going to use this other one here. So okay. So let me use this. So MATLAB online OMX. Mm, okay, no, I have to reestablish my password. Let me let me put here.
Teacher,
Yes,
my partner Roberto
yes.
wrote something in the
Ah,
chat.
in the chat, let me check. What this says. Yo acabo de crear una cuenta con mi correo. Perfect. Can you share, please, Roberto? Let me try with this command. I already received the email. Otherwise, I will ask you please to share your computer. But this is the code for me. So let me put. I am going to write the new password. Okay. Let's put next. Apparently, it's already updated. So let us see. The problem is that we nowadays have so many passwords. Here we are, and so many accounts that it is very difficult to remember. For me, it's very difficult now to remember all my passwords. So sorry about that. So here you have two options. You can open Matlab online or you can download it. Okay. For instance, in my case, I have already downloaded the Matlab and I have this desk version. Okay. This is my version in my computer. I have here the Matlab in my computer. Okay. But you can open here online. And it is exactly the same. The good point about this online version is that you don't use resources of your computer because you are using in a cloud this version of the MATLAB. So all that you are using is the resources are in the cloud. Okay. So can everybody access this MATLAB online?
Yes.
Okay. So I am going to put the code. I am going to copy this code and put it on the chat. And you are going to paste it in the MATLAB, okay? So let me copy this. Okay. Let me put in the chat. Okay. How can I attach a file here? Mm, mm, mm. I think that it is here. Okay. I am going to attach this script. Okay. So I am sending you the script. So please open this script on your computer, on your Matlab online. If you try to download the version, you can do it for both for Windows and for Macintosh. Okay, but I think that it takes a little bit of time to download the desk application. So perhaps the more convenient thing to do now is just to use the online version. Okay. Well, I am going to run this script. So let us run this script. Here we are. So it will create five different figures. I will explain each of them to you. And you can see here in the command window the results of the calculations. So please run the script that I have put on the chat here in Teams. Run the script, and you are going to have these results. Okay. So look, automatically this script, because it recognizes that we are going to have a full factorial designs 2 to the power 3 with replications, which is exactly what I have put on the Word file. So let me look for the Word file here. Okay. So here are the combinations, right? Minus one, minus one, minus one. But this is automatically generated by the MATLAB commands. So each experiment is replicated 2 times, and here are the distances recorded. Do you remember that I put 2.1, 2.3? Well, here the order is a little bit different, but it is exactly the same. Here the replication is for the same experiment. It's being carried out 2 times, one after another, and in this case, it has recorded the two values, 2.1 and 2.3, which correspond to this very first experiment and experiment number 9. 2.1 and 2.3, right? Then the following is 3.0, which is this one, and the following is 3.2, which corresponds to the experiment number 10 in our table, okay? And so on. It is exactly the same pattern, okay? You can follow the pattern, and you can see how this is organized, okay? And here is the building the factorial model. Okay, so we are carrying out a linear regression model where the distance has to do with the different coefficients of these variables. Okay, so here we can say that the distance, I am going to put the mathematical model. Do you remember in Excel last week that we did exactly this some similar exercise? So the formula will be that distance equals the intercept, which is, let me see if this is statistically significant. All of them, but the last two are statistically significant. How do I know? Because these values are much lower than 0.05. Okay, all of these are lower than that critical value. So apart from the last two, all of them are relevant. So I am going to put the mathematical model. So the distance equals 3.8188, which is the first coefficient, this one, okay? Plus, I have to put plus the following coefficient, which is 0.94375 times, I have to put times the wing. So remember the wing is related to the first factor, A, wing length, okay? I am going just to simplify and use wing. Then plus 0.43125 times the second variable or factor, which is the weight. Plus the following coefficient, which is 0.73125 times the angle, the launch angle, times here let us put 0.25625 times the wing times the weight. Perfect. And finally, plus 0.18125 times wing times angle. That is my model. Okay, so let me put here. I am going to put this in bold. And let me put this in the center. That is my result, okay? I have taken these coefficients from the analysis carried out in the Matlab software. So look, the R squared is 0.996, which is very close to 1. And the p-value is much lower than 0.05, which that means that this is a very good model. This is a very good model for predicting the distance based on the experiments of the 16 experiments that I carried out. Okay, that is the interpretation of this table. Let us now continue with the ANOVA. So in the ANOVA, again, you can look at the p-values here, and you can see that all of them, both the last two, are important for the model. So that means that these variables and their interactions help me to explain the distance of the airplane, right? In other words, if I modify some of these variables or these factors, yes, the airplane is going to either fly longer or fly a shorter distance, right? If I modify, because they matter, they are very important. So this is the the result that I can see in this table. Okay. What is the interpretation? Look, the interpretation is that the wing has a significant effect. This variable strongly affects the response variable, which is the distance, okay? How do I know? Because the p-value is practically zero, okay? It's a very small p-value. We can see here, which is 1.6 to the minus 14. So it is zero practically. Okay, what else? So I am going to put this interpretation here. Let us put here this interpretation in the results analysis. So let me paste. Okay. So the wing has an important influence. The weight as well. The term weight, I am going to put in bold, also has a significant effect. This variable strongly affects the response, okay? Again, because the p-value is very close to zero. What happens with the angle? The angle is also an important variable and has a significant effect. What happens with the interaction between wing and weight? Okay. There is also a significant effect, and this variable strongly affects the response. Again, I know that because of the p-value. Look here, the final important term is the wing with the angle, which also has a significant effect because of the p-value is also very small. But what happens with these last two? They are not significant. We already knew that, right? We already knew that because we observed the table and the values are greater than 0.05. Look, if I go up, these two values, the final two, these two are greater than 0.05. That means that this doesn't matter. Weight and angle doesn't matter, and wing weight and angle doesn't matter. Okay? That is the interpretation here. This is not significant. Let us put it in bold. And the interaction of the three variables, A, B, and C, is not significant because of the p-value is very large number in comparison with the 0.05. Okay, that is the interpretation. Okay. Residual analysis. Well, random residuals indicate a good model and patterns indicate model problems. Let us now look at some of the graphs, okay? Okay. So this routine generated these 5 figures. So let me put here. Okay. So in figure number 1, let me copy this copy figure, and I am going to paste here. Okay. I am going to put it in the Word document. Okay. This is figure 1. Figure here, figure 1. Which is main effect plot. Okay, here. Look, the meaning of this figure is that you can see that the greatest effect on the flight distance is related to the wing. The wing has the biggest effect. Look, if I put here my mouse, you can see the values, okay? So it is 1.88, okay? That is the effect that it is this variable is having in the flight distance. And as you can see, it is closer to the right hand of the screen, okay? It is closer to the right hand. It is very, very close to this extreme. In second place, the second variable that has the greatest effect is the angle, the launch angle. And you can see here the value, which is 1.46. That is the second one. And the last one, the third, is the weight, because the effect is only 0.72. Okay, so that is the order. That is the order in this case of the factors. So the greatest effect is related um, to the wing. The second is the angle, and the third is the weight. And look, you can see that in the model. So if I check, look, the wing has the very big coefficient, which is 0.94. That is the coefficient of the wing. So you multiply the wing for times this coefficient, and you are going to have a very big number. Okay. The second place, look, is the angle. Do you remember in this graph? Look, the angle, the coefficient is 0.73. I am going to underline this. So this is lower than 0.94, and it is between the greater and the smaller. So the third one is the weight, and look, the coefficient is also the smaller. Can you see? So we have this graph, this figure, which is very helpful, but imagine that you don't have access to this graph, okay? You could see in the model, in the distance model, the order the order of influence of the factors. The most influential factor here is the wing length. That is the most influential factor. How do I know? Because this coefficient is very big in comparison with the other coefficients. Okay. Well, let us now look at figure number 2. So this is figure 1. Let us now look at figure number 2, which is this one. I am going to copy the figure and put it here. Okay. Oh, sorry. Uh, copy the figure number 2 here. Okay. Copy figure and paste. Paste. Okay. So this is figure number 2. Let us enter this text, figure 2. Okay. And the name of this figure is interaction between wing versus weight. Okay, perfect. So this is figure number 2. Okay. Well, let us go back to the model. Here we are. Okay. What we can see here is that, yes, there is an interaction between these two variables. How do I know that? Because I have the wing here in blue. This is the blue line with this small circle. And there is a intersection. If I put a vertical line here, what I can see is that they two cross. So if I put a vertical line here, I can touch first this blue small line and this let's say orange line. Okay, so that means that, yes, there is a interaction between the wing and the weight. Okay, and you can see here in this term, you have this coefficient and the interaction between these two. Again, I can do it here, and I have also this interaction. Okay. What about figure number 3? Look, in figure number 3, which is related with the wing and the angle, let me copy this figure, copy, and I'm going to put it down there, here. So let me copy and paste. Perfect. So in this case, again, there is interaction because they two cross. If I put a vertical line, I can see that they two are crossing. So let me put the name of the figure, figure 3. So here we are, figure 3, which is the interaction between, in this case, it will be wing versus angle. Okay, perfect. So let us now move on to figure number 4. Figure number 4 is related with the weight and the angle, and you don't have any crossing. Look, you can see here how they cross, but in this case, they do not cross to each other. There is no interaction because one is very close to the right-hand side and the other is very close to the left-hand side. So there is no crossing between these lines. So that means that there is no interaction. So let me copy this figure. So I am going to put it here, paste. So let us put here the title of this figure here. So let me center the text. So this is figure number 4. Exactly, interaction between weight versus angle is not significant. So let us put in the others that they are significant. These are significant, significant. These are significant. And the other is as well significant here. Significant. Okay. Well, and finally, the last figure is this one. And this is the residuals versus the fitted values. So let me copy this figure. Copy. So I am going to put here paste. Okay. So let us put a name of this figure, figure 5. These are the residuals versus fitted. Okay. What does that mean? That means that if I use this model here, so remember, if I use this model, I am going to get a result, okay? And I have to calculate the difference between the result and the value that is given with this model. So let us do it. Let us do it. Okay, so let me put this model here. Okay, I am going to open a new script. Okay. So this is a new script, okay? So clear all. Close all. CLC. This is to clean the window and things like that. So I am going to put like that, the model. Distance equals all these values. Here we are. Here is the model, okay? So I am going to put here wing, which is my first variable. And I am going to put -1. I am going to put here weight, which is as well -1. And I am going to put here angle. Again, it is -1. -1, okay? So here is the distance. That's it. So let me save this. I am going to put this airplane model. Save. Okay, so let us run this this script. Sorry, I am going to erase this in order for me to have the result on the screen. Here we are. So look, the distance, the estimated distance with these three values, -1, -1, and -1, is 2.15. So let us look at the actual result. Okay. 2.1, okay? When I put -1, -1, and -1 in this model, my result is 2.15, but the actual result is 2.1 here, and down there is 2.3. So the residual is the difference. So let us put here the residual. I am going to put here residual one. I am going to put it will be a 2.1, which is the actual value here, minus the distance. And residual 2, it will be the second value of the replication, which is 2.3 minus the distance. Okay, so let us run it again. Look, one residual is minus 0.05 and the other is 0.15. Okay, because the actual value is 2.3 and the result of the distance is 2.15. So the difference between these two values, it is exactly this quantity, 0.15. Okay, let us now look, for instance, at rule number 8. Rule number 8, which is this, the three values are positive, +1, +1, and +1. And the first result for number 8 is 6.2, 6.2, and for the second residual is 6.4. Okay, so let us now run with this new information the script. So run. Look, the distance, the calculated distance with the model is 6.3626, and the first residual is minus 0.1626, and the second residual is 0.0374. Okay, so if we go back to the graph, to the figure number 5, these are the residuals, okay? These values, this 0.1626, it should be somewhere here. This other value, 0.0374, it should be somewhere here, okay? So these points, when you plot them in the graph, show you how good your model is. If they are spread all over the place, that is a good model. But if you look a pattern, if you identify a pattern in these points, that means that the model is not good, because it is always giving you the same exact result. Okay, that is the interpretation of these residuals versus fitted. Okay, and that's it. So we can now move to the step number 7, which is the conclusions. Do you remember the step number 7? Here we have the steps here. The conclusion. What is the conclusion of this experiment, of the airplane experiment? Well, the conclusion is that, therefore, wing length and launch angle matter. So these are two very important factors in order for the airplane to reach a longer distance. Okay, you can tell, you are the analyst and you can tell the decision maker, look, if you are going to design an airplane, be very careful with the wing length and the launch angle, because they matter. They are very important If you want to win the competition, look very carefully at these two factors because they too are very important for your experiment. Okay, so let us now save this. So any questions so far? Do you have any questions about this experiment? We are going to move on to the second experiment. Any questions? Everything okay? Well, perfect. So if everything is okay, so let us summarize this uh, in this conclusion. I am going to put this in a table. So let me put a table here. Insert table. 5, 2 times 8. Okay. So in the results and the interpretation. So in terms of the significant win factor, that means that the wing size strongly affects flight. The second point is the significant interaction. In this case, the interaction has to do with the, let us go back, wing and angle, okay? You can see in the model, you have this interaction and this interaction. You have two interactions. Okay. So let's go to the table. Significant interaction, it will be wing versus weight and wing versus angle. These two interactions are important. So when you have a large p-value, that means that the variable is not important. And if you have a strong r to the power 2, strong r to the power 2, r squared, the model explains behavior well. This is in British English. Let us put in American English. Okay. So this is a square. So I am going to put this as a power. Here we are. Okay. So let us put this table. Let me choose here. Here and here. Okay. So in conclusion, we can say here that full factorial designs are ideal when the number of variables is small, when the interactions matter, and when we want a complete understanding of the system that we are analyzing under analysis. Perfect. Okay, so that will be our conclusions. Okay, perfect. So let us now move on the case number 2. Case number 2, which is related to the mousetrap car. Here we are. So let us do exactly the same, following the 7 steps that we have here. Okay, so let us start with the step number 1. Step number 1. So this is determining. Here I have missed n. Determining experimental objectives. So I am going to copy. I am going to paste it here. So what is the objective now? So the objective is to optimize travel distance. Again, it is very similar travel distance while minimizing the number of experiments. I don't want so many experiments. I just want a few experiments because I don't have time and I don't have the resources. I don't have the money to build 16 different cars. Okay, for instance, in the airplane, it doesn't matter because it is just paper, right? I can have a paper and I can fold it and so on, and I can throw it and launch it. But in the case of the mousetrap, the cost matters, the money, because you have to spend a lot of money in order to design different cars, okay? So I have to reduce the number of experiments, okay? So step number 2, it is here. Identifying, so let me put it here. Okay. Step number 2 is identifying responses, outputs, and the measurement system. Okay, so the response, in this case, as I said, is the travel distance. And I will use meters as well in order to measure it. Perfect. Step number 3, and I am going to copy this. Identifying, paste. Step number 3, identifying input factors to study along with levels. Perfect. So let me insert a table here. Okay, so I am going to put here the factor, the low level, and the high level. So the factor, first I will have the arm length, which is 15 centimeters and 30 centimeters. Okay, the wheel diameter, in this case, it will be 8 centimeters and 15 centimeters. Okay. Then I am going to put here the axle friction. It's a new variable, which is high and low. And finally, I am going to use the vehicle mass, which is going to be 300 grams and 600 grams. Perfect. Okay, so let me put this in a beautiful way. Okay, here we go. Perfect. Okay. So that is step number 3. Okay, let us now move on to step number 4. Step 4, I am going to copy this, control copy. I'm going to paste it, choosing the right design. Well, in this case, because I want to save money, I don't want to carry out a lot of experiments, I am going to choose the fractional factorial design. Okay, fractional factorial design. Okay, so what does that mean in practice? In practice, that means that instead of running a lot of runs, let's say here you will have 2 to the 4th power. So let me put it here. 2 to the 4th, which is, let me put this as an exponent. So let me put here 2 to the 4, it means 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. That will be 16 different combinations, okay? From low, 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 low until high, 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 okay? That will be the total number of combinations. But I don't want to spend a lot of money in this case, okay? So I am just going to use a fractional experiment. So that means I will cut this by half. So a fractional design implies 8 runs, 8 different runs. Only 8 is a fractional. I don't want the 18. So that is the right design because I want to save money again. Okay, perfect. So let us now move until step number 5. Step number 5. Step 5. I am going to put here, which is running the experiment. So in this case, I am going to put the table. So let me put here insert table. Insert table, which is 8. Let me put here insert. Six columns and 9 different rows. Okay, accept. Okay. So here I'm going to put the run. I am going to name the variables A, B, C, and D, and the Y, which is the response, which is the distance. So let us see what A means. A means the arm. A is the arm. Equals arm. B means the wheel diameter. C means the axle. So is the axle. And D is the mass, the vehicle mass. Okay, the mass. Okay. So let me put this in a beautiful way. Okay. So I am going to have 8 different runs. So, okay, so I am going to put 1, 2, 3, 4, 5, 6, 7, and 8. Only 8 because it is a fractional design. I don't want the complete experiment, but the a fraction. Okay, so only one part. Okay, so look here in this case, the variables again. Let us remember that low is -1. I'm going to put it here -1, and high means +1. So in design of experiments, the values that I am going to put here in this table are the default variables for a fractional design. So you take them for granted. So these are the values always, okay? In a fractional design, these are the values always. You don't have to worry about where I am going to get these values. No, this is the default values in a fractional design. So I am just going to put it here. So it will be 1, -1, 1, and -1. That's the first experiment. The second experiment, it will be -1, -1, 1, and 1. Okay? The number 3 experiment, number 3, it is -1, 1, -1, 1. Perfect. The next one, fourth, it is -1, 1, 1, and -1. Okay, we are already half of the way. Perfect. Let us now move on to the fifth run. The fifth run is 1, 1, -1, 1. So let me put is 1, -1, -1, 1. Perfect. 6, it is 1, -1, again 1, and -1. The seventh, it is 1, 1, and then -1 and -1. And finally, the last, it is all of them 1. Perfect. Okay, So this is the design for this factorial experiment. Okay. Okay, and let us now put the distance. Imagine that I already built these 8 different cars. I have 8 different mousetrap cars, and I record the distance in this table. And let us suppose that the first distance is 4.2 meters, the second is 6.1, then it is 5.4, then 8.0. Now it is 3.8, then it is 5.9, then it is 4.5, and finally it is 7.2. Okay, these are the distances that when I tried the 8 different experiments, I can record from all the cars. Okay, these are the cars. Okay, so let us now move to the step number 6, analyzing the results. So step 6, which is analyzing the results. Okay, I am going to leave here in blank. Then we are going to go to step 7. So I am just putting, and I go back to the Matlab. Step 7, which is the conclusions. Okay. Okay, so let me go back to the Matlab. Okay, so I am going to put in the Teams again the following script. So it is fractional factorial. Okay, fractional factorial. So please download this script, this file, and run it in your Matlab. So it is fractional design. Here we go. You can download this script, please, and run it in the Matlab, either online or in your computer. Okay. Okay, so let us go here. Okay, so if you open this script on your Matlab and then you run it, you can see here that we are using the command fact. Okay, so let us run this. If I copy this command, look, these numbers are exactly the ones that I put on the table in the Word file. Okay, so if you compare, let us put here. If you compare this table, this design, this is the command fact that allow us to create this table, which is exactly this one, automatically in Matlab, because this is a library that Matlab already has. Okay. So let me run this routine. Okay. So let us go to the analysis of results. Okay. I am going to write it here in the Word document. So if you run this script, we carry out exactly the same analysis as the previous case. So these are the coefficients. What are the important coefficients here? Look, you have the intercept, which is the independent term. You have the wheel and the friction. What happens with the arm and the mass? They don't matter. They don't matter because these p-values are very large. So what will be my model here? I am going to write it. So distance, let me write here distance. Sorry, distance equals. The intercept is a very important coefficient, which is 5.6375. This is the independent term plus. This doesn't matter, this one, because the p-value is very large. This is not important, this factor, but this one, it is important, will. So it will be 0. Let me write it here, 0.6375 times, okay, and the variable of interest, which is will. Perfect. Times. So here, friction is also important because I am comparing this p-value with the 0.05. So friction is always important. So let us put here the coefficient, which is 1.1625 times friction. Well, let us put here, instead of axle, I will put friction, okay? Here, friction, in order to have coincidence between the Matlab and the Word file, friction. Okay? And that's it. The mass doesn't matter because this value is larger than 0.05. So this will be my model, a very simple model. But look, because here we are. I had 4 different variables, which are, it is a considerable number, okay, of variables. In the previous example, I had three variables, but now I have 4. But look, when I carry out this fractional design, what I can see is that only 2 of them matter, which is wheel and friction, okay? What else can I say here? I have an R squared of 0.975, which is very close to 1, so it is a good model. And the p-value is lower than 0.05. So this is a significant model. It helps me to explain the distance. Okay, perfect. So here, again, we have, let me go back to the, what we can see here is that the arm doesn't matter because this p-value is very large, and the mass doesn't matter. Only wheel and friction, you can see here the coefficient, and it is exactly what we had here, wheel and friction, okay? That is the interpretation, okay? Perfect. And let us now look at the figure. So the figure, let me go to the figure. Here we are. So I am going to copy the figure here. Sorry, figure here. So let's copy figure. Okay, paste. and I am going to put the title of this figure. Here we are, figure 1. Well, it will be figure 6, right? Because the previous figures are from 1 to 5. Well, figure 6 is the Pareto effects. So here you can see that uh, the friction, which is the, sorry, in the model, look, friction has the greatest coefficient, okay? So the impact of friction in the distance is very important. That means that the car is going to travel farther away, and you can explain that because of the axle friction, okay? So if you have a small axle friction, then the car will go very far away. What happens with the wheel? Again, is the second place in this case. Uh, let's say the height of the bar is the second place. So that means that the wheel is also an important factor, and not so much the arm and the mass. The mass is very insignificant. As you can see, it is very insignificant in this case. Okay, that is the interpretation of this second experiment. So let me go back to the Word in order to draw the conclusions. Okay. So, okay. So let me delete these spaces. And I had an error down up there. Let me correct this word. The step number 1. Here, determining there is an N missing here. Okay. Objective. Okay. Everything is. I am doing this in real time. So that's why I have some mistakes sometimes. But if I can see them, I correct them immediately. Okay, so let's go down here. Okay, perfect. So what can we say here in this second case study? Well, uh, let us put the full factorial design would have implied 2 to the 4th experiments. So let us put here 16 experiments. Okay, so let me put in the right notation, 2 to the 4th, the power 4. So it will be like that. Okay. But a fractional design, fractional factorial design, only implies 8, which is half of the 16 experiments. So if I don't have so much money, if I don't have so much time to carry out experiments, I can always run a fractional factorial design, okay? Fractional factorial design. Okay, so this is perfect for artificial intelligence parameter screening. So if I can look or if I can find out which are the important factors, I can use a fractional factorial design. As you can see here, I can quickly see that the two factors that matter the most are friction and weight. That's it. And I did it in a very faster way. This is also perfect for expensive experiments because this the design save money and time. So if you have this problem, then you can use this type of design, and then you can have a fast prototyping. Okay, so that is some of the conclusions that we can draw here in this second experiment, second case. So let us summarize this in a table. I am going to share with you this file once I have finished. So let us put here a table. So it will be 5 times 2. Okay, so you have an observation. And here you have the meaning or the interpretation. Okay. So the largest coefficient is the most influential variable. A small coefficient it means that this variable can be ignored. And then a high R square is a good predictive model. Finally, the reduced runs, well, are design of experiment efficiency. That is what we can say about this second case study. Well, let me put this, and that's it. Okay, so that is the second case. And finally, we are going to look at the third case, okay? Our third case study. Any questions so far? Again, this is going to be recorded and put it in my YouTube channel so you can see later on all the explanation. Okay, so let us now move on the case number 3, which is the concrete beam. Okay, so let us put here in bold concrete beam. Okay. Okay, so let us now move the same 7 steps. Remember, these are the steps to carry out design of experiments. If you follow these steps systematically, you are going to be very good. Okay, you are going to have 100 points. So first step number 1. Step 1. Determining experiment objectives. Okay. So in this, the third case, the objective is to optimize the compressive strength. Okay, that is our objective. Do you remember we can play with the mix of cement, other rocks, the water, and so on, in order to have a stronger concrete. You uh, you start playing with these materials, and then you can have a combination that is perfect to resist the loads in the beam, in the concrete beam. Okay, step number two. Step two, identifying the outputs and the measurement system. So control copy, control paste. So let me put here paste. Step number two. Perfect. So our response will be response. The compressive strength, and we are going to measure that in megapascals. Okay, perfect. Step number three. There are 7 steps, remember. We are in step number three, which is identifying the factors and the levels. Step number three, paste, identify the factors and the levels. Okay, so let me put here a table. In this case, we are going to use only 2 factors. So this is the factor, and this is the range. So look, the first factor will be the water cement ratio. And we are going to have the following range from 0.35 until 0.60. Okay. And then the curing time. Curing time refers to the process where once you have put the concrete inside, you have to add some water in order for the chemical reaction of the concrete to go smoothly. Because if you don't add this water, the concrete gets very hot. So it burns. If you touch the concrete, it is like fire, okay? Because it's very hot. Because the reaction, the internal chemical reaction in the concrete produces this heat. Okay, it is very warm. If you touch the concrete, it is very warm. So you have to mitigate this temperature because the temperature can rise a lot. You have to mitigate the temperature by adding water, and the water starts getting down the temperature of the concrete. And this process is called curing of the concrete. And you have to use the curing time for several days. So in this case, we are going to use from 7 until 28 days. Perfect. So let me put this in a beautiful manner. Here we are. Excellent. Okay. Okay, so number 4, choosing the right design. Okay, let me copy this. Number 4, step 4. Paste. Choosing the right design. In this case, we are going to use the response surface method. Response surface method, which acronym is RSM. Okay. And we are going to use in this case, instead of having a line, a linear model, we are going to have a curve, okay? Because it is going to be a equation with the second degree, okay? It is going to be a second degree equation. So let us put that here. Is used because the real system is not linear. A concrete behavior implies a curvature, a saturation, and it has an optimum point. I think that there is a optimum combination of materials that leads to the uh, best compressive strength. Okay, you can optimize this mix in order to have a very strong concrete. Okay, so we are going to use the response surface design. Step number 5. Okay, step number 5. So let me copy, running the experiment. Okay, so let us paste step number 5. Okay. So I am going to build the table. So let me put this here. Okay. So here we are going to have 3 different levels for each of the variable. So let me write it here. I am going to insert a table. So it will be insert table. And I am going to have 1, 2. So it will be 1, 2, 3. Let me see. 4. So it will be 4 columns. And I will have 10 different rows. Okay. So let me put this like this. Okay, so let us put the run number 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. Then I am going to have here the water cement relation, which is water cement. And here I am going to have the curing time. And finally, I am going to have the strength. Oh, sorry. The strength. Okay. So let us put the combinations. For the water, I am going to use 0.35 three times. That is the lower limit of my range. You can see here 0.35. Then I am going to use 0.60, which is the other limit. 0.60, 0.60. And here in the middle, I can use a value between 0.35 and 0.60. Let us use 0.45. Okay, I'm going to use 0.45 and 0.45. Perfect. I have my three different values, 35, 45, and 60 for the water cement ratio. And now in the cure, I will have three different times. Remember, I have between 7 and 28 days. So I will use three values. It will be 7, 14, and 28. 7, 14, and 28. And 7, 14, and 28. As you can see, this is a very systematic way, okay, to do the experimental design. So if you do it very systematically, the probability of having some error decreases because you are having this in a good order. Okay. And finally, let us put the strength. So imagine that I have already in my laboratory, I built the different mixes of concrete. The first one uses a water cement ratio of 0.35 and the curing time is 7 days. Okay. So imagine that the strength that in megapascals that I am going to record in this case is 38. For my second experiment, it's 42. The third is 48. Then 32, 39, 44. All of these measures come from the laboratory, okay? I have to carry out the experiments in real life, let's say. And when I do that, then I am going to be able to build this table, okay? Because I am having the information from the laboratory. Okay, so let us save this file. Okay, so step number 6, step 6 is related to analyzing the results. I am going to share with you a new script of Matlab. Analyzing the results, okay? And again, step number 7 will be the conclusions. So step number 7 will be the conclusions. I left this in blank. Okay. So let me share with you. Okay, so let's go to the Teams here, and I am going to share this new script. Has everybody be able to run the previous two scripts? Did you have any problem with that? The third script is called response surface method. Okay, it is the third script. You can download them from here, the chat in the Teams. Okay, so okay, let us run this script. Okay, you are going to have these figures. Okay. So let us analyze the results. That is step 6, okay? Here, if we see at the coefficients of the model, look, this is a second degree model, okay? This is the strength depends on the water cement times curing and the water cement to the second power and the curing to the second power, okay? So let us see how relevant are these coefficients. So I am going to write the model. Let us center this, and I am going to write my model. So the strength, here we are. So the strength equals, look, the intercept is not significant. How do I know that the coefficient of the intercept is not significant? Because this p-value is very high. If I compare this value, this one, with the 0.05, which is the limit, I can see that this is much higher than that critical value. So I don't include in my model this intercept. I don't include it. Okay. What about the water cement? Again, it's exactly the same. It is this 0.12 is greater than 0.05. But what happens with the curing? In this case, this is significant because 0.02 is lower than 0.05. So I include in my model. So the first term to include will be the curing. So the coefficient is 1.3195 times curing. Okay, perfect. Plus, what happens with the next combination of factors? They are not relevant. You can see that they are not relevant because this p-value is very high. So you ignore that combination. Let's go to the following. The following, it's important, yes, because it is 0.03, which is lower than 0.05. So I take into account in my model. So what I am going to put is the coefficient, which is this one, minus 100. So instead of plus, I will have to put minus 173.33 times water cement to the second power. So let us put water cement to the second power. So let us put here. And I am going to use the correct nomenclature, second power. Okay. And finally, yes, no, the last one is not relevant because it is 0.06 and the critical number is 5. So this is 6. As a conclusion, the last term doesn't matter as well. So that is my model. That is my model. Okay. It's a very simple model. Here we are. Perfect. So let us see. The R square is 0.995, which is very close to 1. That is a very good model. And the p-value is 0.001, which is again a very good value. And look, this when I plot this, I can get these figures. Figure number 1, let me copy. This is the surface, right? Is the surface. Copy figure. And I am going to paste it here. This is the surface. So figure 7. Sorry, figure 7. It is the response surface. Okay, what does that mean? Look, in one axle, you have the different combinations of water cement, okay? 0.35, 0.4, 0.45, 0.5, and so on until 0.6. And on the other axle, you have the curing time, which is 5 days, 10 days, 15 days, 20, so on until 30 days. Okay, that is the maximum value in this axle. And in the vertical axle, you have the strength. So as you can see, in the yellow color, you have the optimum value. What is the optimum combination for getting a very strong concrete? You use 35 as a water cement ratio, so 0.35, and you use the curing time of the 28 days, the maximum curing time. So that means that if you you use uh, a great quantity of cement, but you start adding water constantly one day and the other, one day and the other until the day number 28, this concrete is going to be a very strong concrete, a very good design. Okay, that is the result that we are getting from this analysis of this experiment. And a different way to see these results, here we are. So let me copy this figure, copy, paste, and the name of this figure is figure, wait, figure 8, which is the contour plot. So it is like if I was watching the same surface, but from the very top, okay? So imagine that I have a camera at the top and I take a photograph of this surface. What I will see is this. And you can see here the colors, okay? The maximum value you can get is 45 megapascal. which is in this corner at the very top in the right hand side. And the combination is 0.35 and 28 days of curing time. Okay. So let us put here the conclusions. So let me move back to the, I have already copied. Okay. Okay, so let's go to the conclusions in the third and last case of today's lecture. So let us put here a table quickly. So insert table. Here we are. So let me put here in this way, in a beautiful way. Okay. So you can see the pattern. And here in this column, we are going to have the meaning or the interpretation. Okay. So the curvature, that means that there is a nonlinear response. Perfect. The peak region or the maximum represent the optimal conditions. Then the contours are regions of equal strength. Finally, the interaction are, the meaning is that variables affect each other. So we do have interactions here in this model. So that means that yes, there is a relation between the water cement ratio and the curing time. Okay, that is the conclusion. So to sum up the lecture, we can say the following. I am going to insert again a table. Okay. Experiment type. Let us put DoE, design of experiment type, and when you should use this type. Okay. So keep in mind these three aspects. So full factorial you use with the small systems. And it is very useful for interaction analysis. Then fractional factorial, which is the second that we analyzed. You use them when you want to the screening many variables. If you have so many variables, use fractional. Okay, many variables. And finally, the response surface method. RSM. You use it when you want to optimize and you are in front of nonlinear systems. Okay? That will be the summary of today's of today's lecture. Okay, so I am going to translate this into a PDF and I am going to share it with you. Okay, and I am going to put it here uh, in the Teams. Okay. Mm, okay. So, guys, do you have any question about the scripts, about the interpretation of the results that we just analyzed? Everything is clear? Okay. So I am going to stop recording this video and give me a minute, please. Thank you, everybody, for your presence here.